Well, students, in the last class, we have started our discussion on errors. We have seen that there are two levels of errors that we will encounter in numerical analysis. One is due to the mathematical approximation of the problem that we would like to solve, and that we often call as mathematical error. And another type of error is encountered when the methods are implemented on a computer. This second type of error is often called arithmetic error, and it plays a very important role in our study because it amplifies the total error significantly. Therefore, it is important to understand how this error occurs and how it propagates in our computation. In the last class, we have introduced floating point representation of a number, and also we have seen that in general computers takes a real number not in its exact form but only in a approximate form due to its limitations in the memory. In this connection, we have introduced floating point approximations. One is the chopped approximation and other one is the rounding approximation. Generally, we denote the floating point approximation with the notation FL of X. It can be either by chopped idea or by rounding idea, or it can be anything else. But in our course, if we want to be precise on how we are approximating, we generally consider either the chopped approximation or rounding approximation. Next, let us see how a computer performs an arithmetic operation. This is important to understand in order to get an idea of how the error due to floating point approximation gets into our computation and propagates from one arithmetic operation to the other and gets amplified. Let us denote any one of these four arithmetic operations by the symbol circle dot. Let x and y be two real numbers given to us, and we want to do one or more of these arithmetic operations on a computer. Let us just take one operation and understand how a computer does that operation. So let us assume that we want to do this arithmetic operation where this circle dot is one of these four operations. It can be either the plus, in which case it is x plus y, or it can be the minus or product or division. The first step is get the n digit floating point approximation of the value x and value y. What you are doing, you have a computer, you are giving two numbers x and y to your computer. What it first does is it takes x and makes the approximation, floating point approximation. It has its own way of doing that. For us, it can be either chopping or rounding. In this particular discussion, we are just considering n digit rounding. It really doesn't matter. It can be anything else. So what the computer does is it takes the number x and makes the floating point approximation of that number x as per its algorithm. And also it does the floating point approximation of y, and that is what it will take and consider for the further calculation. It will not consider what you gave as the value of the numbers x and y. It just assumes these two values for the further calculation of x circle dot y. Then what the computer does as the second step is it takes FL of x and FL of y and it does the calculation that you wanted it to do. That is FL of x circle dot FL of y it does. Again, I prompt this circle dot is just a notation that represents any of these four arithmetic operations. It can be a plus here, or it can be a minus here, or it can be a multiplication or a division. Okay, don't get confused with this, just a notation. Once it finds the value of this, then what it does, is it further makes the approximation of that calculated number. That is the floating point approximation of that calculated number. And finally, what you get as an answer is only this. Okay. So you wanted to get the answer for this expression, but you got the answer for this expression. Note that it will be only approximately equal to what you want. Okay. Now the question is, what is the error between these two numbers? What is the difference between these two numbers? And in general, how close this number will be when compared to the value of this number which we wanted to evaluate. Okay, to understand it more clearly, let us take an example. Let us consider the function f of x equal to x into root x plus 1 minus root x. We want to evaluate this function at the point x is equal to 1 lakh, that is 100,000, using a 6-digit rounding calculation. It means what? When I say FL of x, it means if whatever value you give for x, I will take 6-digit rounding for that. That is what it means. So I will take 6 rounding, right? Wherever I write FL of x, it means I have taken 6-digit rounding of the value of x. Don't confuse f of x with FL of x. Okay, I may be even writing FL of f of x. F of x is the value of this function at the point x. FL of x is the 6-digit rounding of the value of any number that you give. First, let us evaluate the function f at the point 1 lakh. That is nothing but 1 lakh into root of 1 lakh and 1, because it is x plus 1 minus root 1 lakh. Actually, we have to do 6-digit rounding to 1 lakh also, but I am not doing it here. I will leave it to you to think why. So let's take the first term, root 1 lakh 1, and that is approximately given like this. It may be having more digits, but I have not written it here because I may not use the other digits. My interest is only up to 6 digits. But remember how I should do this 6-digit rounding. Well, first write it in the floating point representation. Well, I am not writing here minus 1 to the power of s. Okay, that is perhaps confusing me, therefore I don't write it. From the examination point of view, if I ask you to specifically write it in the floating point format, then you have to precisely write minus 1 to the power of s and so on. Otherwise, in a running calculation, you may just avoid writing redundant notations like this. You may even do 6-digit rounding directly here, but I may prefer you to first write it in the floating point form and then do the 6-digit rounding. Sometimes what happens is students will by mistake do 6-digit rounding here itself, but actually you should do the 6-digit rounding in mantissa. Okay, remember the mantissa is nothing but you are writing this number in this form, with the important point is that D1 should be not equal to 0, and you don't have any non-zero number before the decimal point. So it's always better for you to first write it in the floating point form and then do the 6-digit rounding. That will avoid unnecessary mistakes. Okay, so once you write this, it's very clear how to get the 6-digit rounding approximation of this number, and that is given by this value. Since the 7th digit is less than 5, we just chop the rest of the digit starting from 7th digit onwards. If that was something greater than or equal to 5, then we would have added 1 digit to the previous number. So therefore, the floating point approximation of root 1 lakh 1 as per our definition of FL is going to be this. Whereas the actual number is in fact something more than this. There is more here, but floating point approximation of that number as per 6-digit rounding is this. Similarly, the next term, root x, remember x is 1 lakh, therefore root x and its floating point approximation. Again, root 1 lakh you take and then write it in the floating point representation and do a 6-digit rounding, you will get this. So as I told you, we have done the first step. Okay, so you take the numbers, that is root 1 lakh 1 in this case and root 1 lakh in this case. Remember, x, if you chop, it becomes the same. Okay, because it already has 6-digit. So you don't have any approximation scope in that part. It comes as 1 lakh only. If it was more, then it would have been an approximation. But further calculations are involving certain approximations here. Therefore, what our computer will do is it found this, and then it subtracts. And whatever number comes as the output of this subtraction will be further approximated using 6-digit rounding, and that is given by this value. Now, finally, you have to multiply that number with x, that is 1 lakh. So, FL of 1 lakh is again 1 lakh only into this, and whatever answer comes, that will be again made a floating point approximation. So you have the floating point approximation of 1 lakh, that is x, FL of x. This is FL of x is this, and your already computed value in this bracket is this. You multiply both and take a floating point approximation, that is 6-digit rounding, you get this value. Therefore, using 6-digit rounding, we get the answer as 100. The same if you do, instead of 6-digit rounding, if you do with chopping, what is the value that we will get? Well, I have done the calculation, but I have not shown here. Using 6-digit chopping, the value of the function is going to be 200. You can see that the kind of error between these two numbers itself is so huge. What we are doing seems to be not a very significant approximation. It has an error very small in magnitude, but the final answer, you can see that there is a big difference between the numbers. Now the question is, which one is more close to the actual value? Well, we will come to this part little later. Let us go on with other definitions. We will keep this in mind and answer it later. The next definition is the mission epsilon. The mission epsilon of a computer is the smallest positive real number delta such that FL of 1 plus delta is greater than 1. Remember, how will you write 1? 1 is nothing but 0.1 into 10 to the power of 1, right? Suppose you take delta is equal to 0.0001, then that can be written as 0.1 into 10 to the power of minus 3, right? Well, how to find 1 plus delta? Here we just have to add these two numbers. Of course, we can easily add it, but the question is how to add it with the floating point representation notation. To add these two numbers, what you do is you just write it in the form 0.0001 into 10 to the power of 1, so that their exponent part matches with each other. Well, this is not in the floating point representation. This step you are doing just to do the addition as a human being, not as a computer. Okay, so you write like this, and then now you add these two. So you will have the floating point representation of this number as minus 1 to the power of 0 into 0.100001 into 10 to the power of 1, right? Now, suppose you are working with a computing device which always does 4-digit rounding. It means it just takes only this much. Assume that it is working with the decimal. Generally, computers work with binary. Just imagine that our computer is working with decimal, then do this calculation. Then what your computer does is it will simply take it as -1 to the power of 0 into 0.1 to the base 10 into 10 to the power of 1. That is simply equal to 1 only. So for such a computer, although you are asking it to perform 1 plus delta, which is not equal to 1, but it understands this number as just simply 1 only, right? So that is what the basic idea of machine epsilon. The machine epsilon of a computer is the smallest positive number delta such that the floating point approximation, whatever it means for that computing device, the floating point approximation of 1 plus that number delta is greater than 1. Thus, you take any real number less than delta, your computer will understand it as simply 1 only. It doesn't know that it is something greater than 1. So such a number delta is called the machine epsilon. Let us introduce the notion of error now. Obviously, we all know intuitively what is meant by error. You have a number x. Instead of using x in your calculation, you are using some other number x tilde, say. It may be coming from some way or the other, the floating point approximation. It may be chopped or round or whatever. Then the difference between these two numbers is what is called the error. What is meant by absolute error? The absolute value of this is what is called absolute error. Generally, in many books, by error itself, they mean absolute value of the difference between the true value and the approximate value. Now, what is called the relative error? Well, relative error is a measure of the error in relation to the size of the true value. That is, you take the error divided by the true value. That is called the relative error. Again, in many books, it is taken as the modulus of the error by true value. So to talk about relative error, we always should assume that the true value is not equal to 0. The percentage error is nothing but 100 times the modulus of the relative error. We use certain notations in our course. Whenever we say E of XA, it means you have an approximate value to your true value x. Generally, we denote the true value by x and its approximate value by XA. Then E of XA means the error of XA, and of course from our last slide it means true value minus the approximate value. Similarly, EA of XA means absolute error, and ER of XA means relative error. These are the notations quite often we use in our course. Next, we will introduce an important concept called significant digits. Let's take this usual example. Consider our x as 1 by 3, which is nothing but 0.333, and it goes on. If you want to consider XA, which is equal to 0.333 instead of x, which is 1 by 3, then we say that we have considered 3 significant digits when compared to our original number x. I hope you got an intuitive idea of what is called significant digits. You can see that in the original number, you have 333 in the first 3 positions. You have retained that in your approximate number. That is why intuitively you have told that you have taken 3 significant digits when compared to x. Well, this is intuitive. Let us define this concept mathematically. Significant digits Generally, when you are working with base beta, it is called significant beta digits. If beta is 10, then generally we say significant digits. And always we work with beta equal to 10. Let beta be the radix or the base. If xa is an approximation to x, it can be in any way you have approximated. It can be just you considered some number, or it can be a floating point approximation using chopping or rounding or anything. Whatever way you want, you got an approximate value of your original number x. Then we say that the approximate value xa approximates x2 or significant digits if r is the largest non-negative integer such that this inequality holds. Remember, the left hand side is nothing but the relative error of xa when compared to x, and you are taking the modulus of, and that is less than or equal to half into beta to the power of minus r plus 1. Then you say that xa approximates x to r significant digits. What is the idea behind this formula? Well, you solve the exercise problem 7 subdivision 2, you will come to know what is the idea behind this formula. I'll leave it to you to see that. As usual, since we are working with the relative error, we have to assume that x is not equal to 0. As I told you, when beta equal to 10, we simply refer the significant 10 digit by significant digit only. The next keyword that we want to understand is the loss of significant digits. Let us try to understand this loss of significant digits through an example. Consider two numbers x and y given by these values respectively, which can be written in the floating point representation like this. Of course, there is a minus 1 to the power of s, or maybe 0, which we sometimes don't write it. Now, instead of using these numbers in my calculation, I'm going to use these numbers in my calculation. You can either check intuitively, or by putting these values in the above definition, you can see that xa has 7 significant digits when compared to x, and ya has 8 significant digits when compared to y. Well, I don't want to encourage the intuitive idea, but still I'll tell you, you just count 1, 2, 3, 4, 5, 6, 7 digits are exactly matching with your original number here. That can be taken as an intuitive idea to say that xa has 7 significant digits when compared to x. However, care should be taken in making this statement as a rigorous mathematical statement. You better always check the definition to arrive at how many significant digits are there in the approximate value when compared to the true value. It may not always come as merely counting the number of matching digits. Okay, so by checking the definition, we have arrived at these numbers. xa has 7 significant digits when compared to x, and ya has 8 significant digits when compared to y. Now, what we want to do with these numbers, we are interested in finding the difference between x and y. That is to find x minus y. But instead of finding this value, our computer say it computed this value. Just imagine. Therefore, we are supposed to get this number as the answer, but our computer gave this number as answer. Well, it looks as if it is okay for us because we are supposed to get this number with 7 here, but we got this number with 1 here. Now, what is the relative error? You can see that the relative error in ZA when compared to Z is this number, and this you can easily see that is less than 0.5 into 10 to the power of minus 2. Why I made this estimate? Well, I want to see how many significant digits are there in ZA when compared to Z. So I am trying to apply this formula to arrive at the number of significant digits. So I put this to this step for that purpose. Now you can see by looking at this exponent how many significant digits are there in ZA when compared to Z. Well, if you go back to the definition, you see this entire expression was -2 in our case. Therefore, that should be equal to minus r plus 1. That tells us r is equal to 3, right? So, we have 3 significant digits in ZA when compared to the true value Z. You look at what we lost in this calculation. We started with two approximate numbers, XA and YA, where XA had 7 significant digits when compared to its true value, and YA had 8 significant digits when compared to its true value. But after performing this calculation, we see that the resulting approximate value ZA has only 3 significant digits when compared to its true value Z. Here we say that we lost some significant digits. This is the idea. There is a loss of significant digits happened in this calculation. I hope you understood this. This is a very important concept we will be using throughout our course. Again, I'll repeat, we started with two approximate numbers, XA and YA, which were correct to 7 and 8 significant digits respectively when compared to X and Y. Their difference ZA had only 3 significant digits with respect to Z. Therefore, there is a loss of significant digit happened in this process. Now the question is, so what? You see the relative error in ZA and look at how much time it was amplified when compared to the relative error in XA. That is, you find the relative error between these two numbers and compare it with the relative error between Z minus ZA by Z, right? That is this. You can see that the relative error in ZA is 53,581 times approximately the relative error in XA. It means you started with two numbers, but your calculation took only approximate values of these numbers. Whatever may be the relative error involved in them, the calculated value was, its relative error was amplified 53,581 times. A similar amplification even happened in Y also. So you can see that the loss of significant digits is therefore very dangerous. It amplifies the relative error. So you started with some numbers X, XA, Y, YA, and made a computation, and the calculated value ZA instead of Z amplified the error 53,581 times. Just imagine that you are doing such a calculation some 1 lakh times in your whatever model you do. Each time when you do a calculation, the error is amplified with this much times, then you can imagine that your final answer may not be anywhere near to what you want, even though you are mathematically, the method may be very good. Therefore, we have to take this loss of significant digits very seriously in our computation. The loss of significant digits in the process of computation is referred to as loss of significance. Let us go back to our example where we have taken f of x equal to x into root of x plus 1 minus root x. If you recall, we tried to evaluate this function at x equal to 1 lakh using 6-digit, right, And if you recall, the value of f of 1 lakh using 6-digit rounding, we got as 100. And similarly, if it was chopping, we got the value as 200. Whereas the true value is 158.113. So where we went wrong? So you can see that there is a huge error in our computed value when compared to the true value. This is the true value and this is the approximate value that we obtained. So where we went wrong is the question. Well, if you take x very large, you can see that root x plus 1 will be approximately equal to root x. Okay, means they both will be very close to each other in their value. Therefore, when you subtract them, there are certain digits which will get cancelled in the subtraction. And thereby, you are losing some significant digits here. That is where you went wrong. As we have seen in the last example, the loss of significance result in the increase of relative error in the computed value when compared to the relative error in the input value. Now the question is how to avoid loss of significance. Well, we can rewrite certain expressions that we are using in our calculations, if possible, to avoid the loss of significance. For instance, your function f of x is equal to x into root of x plus 1 minus root x can also be written like this mathematically. There is no problem, right? You can easily see, you rationalize it, and you can write this expression equivalently like this. Now, the same 6-digit rounding calculation, instead of having this expression, if I do this expression, means what? The calculator that I used is same, but the expression is, well, mathematically equivalent, but physically they look different. But your 6-digit rounding calculator gave this answer. The same way, every step you do 6-digit rounding, but use this expression instead of x into root x plus 1 minus root x, you use this expression, which is mathematically equivalent. You get this number. If you recall, the exact value was 158.113. Now you got 158.114. So it looks as if it's a magic because we are using calculator is same, expression is mathematically equivalent, but there is a drastic improvement in the error. This is because in this case, there was no loss of significance happening, whereas in the previous case, precisely in this step, we are losing the significant digits. I hope you understood mathematically and intuitively what is meant by number of significant digits and what is meant by loss of significant digits or loss of significance. This is very important because there were many disasters happened in real life. The designers have not taken care of the loss of significance in their software that they used in their designing. You can read an article in this website to see certain instance where loss of significant digits brought big disasters in real life.